Alright, so what I'd like to do in this video sequence is talk about everything you need to know to predict good soaring days. And I'd like to start with the real basics of this and kind of build our way up. You might have been exposed to some of the technical stuff that I'm going to get into, but I want to go beyond that. I want to build a framework where you can really see the intuition behind these ideas. So what we need to introduce first is two things: temperature and dew point. So temperature is easy. That's basically just a measure of the energy a given volume of air has, the amount of energy the molecules have specifically, even more specifically kinetic energy. Basically, the higher temperature, the faster molecules are moving, and we essentially sense that as hotness. So that's temperature. Dew point is a bit trickier. I'm sure you've all heard that term before, but I really want to give you guys an intuition of what this is. Let's start with water vapor, actually. I'm sure you all know in any given volume of air, there is evaporated water. And just to give you a rough idea, at room temperature on a typical day, it would be about 40 grams per cubic meter. So that's the equivalent of roughly 1 gallon of water in the volume of air you'd have in a room, or something the size of a room. That's just a rough idea, but here's the key idea. It's not always a fixed amount. Like oxygen, we, can vary. That's a fixed proportion of oxygen in the air pretty much everywhere in the world at any given time, or nitrogen. But water vapor changes a lot depending on a lot of different things. So now let's say you have a given volume of air, and let's say this is a cross-section of a given volume of air, looking at it from the side. Let's say this is a cubic meter of air, or it could be a cubic foot, it doesn't really matter. It's going to have a limit to how much water it can hold. It's going to have a certain capacity to it. So let's draw that as a line. Let's say right there, that's the maximum amount of water it could hold. If we were like filling this up as a tank, it would, that green line represents the capacity of the water. The rest of it has to be some other type of molecule in this fixed volume of air. It may not reach that capacity, so the amount of water in this volume of air may end up just, being like that. And by the way, this is condensing all the water and like pushing it to the bottom. Obviously, that's not realistic. I'm just illustrating the proportions here, as if we were filling this volume of space up with water. So yeah, it may not reach its capacity, but it has a certain capacity. And the capacity will depend on temperature. So let's say this is 70 degrees, we'll say. The key fact here, the lower the temperature, the less capacity for water it's going to have. I should have drew that at an equal size, but you get the idea. Let's say we have a hotter one here. Let's say this one is 90 degrees. It's going to have more capacity for water. So that's the idea. That's what changes with temperature, is the capacity it has for water vapor. Now again, this has nothing to do necessarily with how much water is actually in there. That has nothing to necessarily do with temperature. What changes with temperature is the capacity. So again, it's not always, the amount of water in these volumes of air is not always going to reach their capacity. So now the dew point of the air. Alright, remember again, so this capacity is going to move up and down with temperature. Let's just take the 70-degree one for now. We'll get rid of these two. If we wanted to know the dew point of this volume of air, again, we know it's 70 degrees, that's its temperature. What that's essentially asking is if the water content were at its capacity. So in other words, we're going to move this capacity line downward to wherever the water actually is. Based on its new capacity, how cool would the air be? So in other words, we start with a given volume of air, a given water capacity, well, a given amount of water in a volume of air. Just based on its temperature, we know where its water capacity is, and we're essentially asking if we were to keep this water content constant. In other words, we're not changing the amount of water that's actually in the air, but if we were to change the temperature such that its capacity would be at the water level, what would that temperature be? In other words, what temperature would the air saturate at if we were to cool it? Hopefully that gave you a good idea of intuition behind temperature and dew point. So in the next video, we'll apply these concepts to air parcels moving up and down in the atmosphere.